The topic for week 1 is principles of fMRI, and I'm going to break it down into 2 lectures. In the first lecture, I'm hopefully going to provide a basic understanding of how fMRI works and give you some feel for some of the physiology and how it got developed. In the second lecture, what I'd like to do is talk to you about some of the uses for fMRI. So in particular, I'm going to talk about using it to identify different neural systems, something that's often referred to as brain mapping. I want to talk about how you can use fMRI to investigate regional information processing. So that is to say, if I'm interested in the amygdala or the hippocampus or whatever particular brain region, how do I use fMRI to investigate how it's processing information? And then finally, I'm going to talk briefly about characterizing interacting brain systems. So one of the sort of logical fallacies that happens all the time with brain systems is the idea that you can identify this bit of cortex is doing X. The reality is that your brain is very, very highly interconnected and the regions are working together. And of course, that is something that you can investigate with fMRI as well. So characterizing those interactions is one of the important uses of the method. Finally, in that second lecture, I'm also going to talk about some of the important limitations of fMRI. Sometimes it's easy to imagine that the device, the tool, is the be-all, end-all. And that's just not true. It's never true. There are strengths, there are weaknesses. Obviously, what I want to focus on for the most of the module are the strengths, but it's really important that you're aware of what the weaknesses are so that you can take them into account when you design your experiments, but also plan other tools to help address them. Okay, so I thought I'd start with this idea from early neuroimaging. This is a figure from a paper that was published in 2013 of an experiment that was reported in William James's Principles of Psychology in 1890. And what happened was there was an Italian neurologist named Angelo Mosso, and my apologies for my pronunciation. I've only ever read his name, so I don't know exactly how it's pronounced. But what he did was he reported doing this experiment where he had a participant lying on a table that was perfectly balanced, so that when that person was lying there at rest, thinking about nothing, then the table was exactly at balance. However, when he then got them to do something cognitive, something that required activity in their brain, it caused the table to tip because the brain started using more energy, presumably it had more blood flow to it, and as a result, the table would tilt, and the more energy they were using, the bigger the tilt. And this was something that William James described as the very first functional neuroimaging experiments. And I just want to imagine what this would look like a little bit. So this is a person lying at rest on this table, thinking about absolutely nothing. And then, for instance, they hear a sentence, "Paula kissed the shy boy," right? And just hearing that sentence, of course, required a certain amount of mental activity, which caused blood to increase its flow to the brain, which causes the head to be heavier and causes the table to tip. Now, imagine they were very familiar with sort of basic linguistics from, say, high school or something, and they could remember something about sort of sentence structure. So they heard this sentence, but they sort of knew something about the sentence structure has a noun phrase and a verb phrase, and they could tease it apart. Well, that requires a bit more mental work, and therefore the table tips further. Or you can imagine that this person is actually a generative linguist. So if you've studied any linguistics, this would be a sort of a Chomskyan linguist who knows something about the deep structure of sentences. So far beyond what you learned in high school about sentence structure. And they can think about this structure. And of course, again, this requires even further activity, which causes the participant to deflect the table even further. And in fact, they probably even fall off. And I just like to thank Matthew Rushworth, a colleague in Oxford, for sharing this set of graphics with me. Let's just think about this briefly, because this is what William James reported in his 1890 monograph. But does this even make sense, right? Like, could this happen? And I think the answer is absolutely not, right? And it's for a variety of reasons. First of all, what does it mean to be thinking about nothing? So the whole premise is that you can get somebody balanced on this table when there's nothing going on in their head. Well, does that ever happen? Is there ever the time where there's nothing happening in your head? No. No, it just doesn't. It's sort of a fallacy that sometimes we think that. You say, my mind is blank or I was unconscious. But that doesn't mean your brain's not active. Your brain's very active. In fact, the amount of energy, the amount of glucose that your brain burns actually goes up when you go to sleep. So the activity is definitely there. So just the basic premise is silly. The second issue is this idea that, well, as you are increasing cognitive load and effort, there's an increase, a rush of blood to your head. Well, let's just think about that, because what do you know about heads? Hopefully, one of the things you know is that your brain is encased in quite a solid piece of bone. Your skull is very thick and very strong, and it's important that that's the case because it's there to protect your brain, which is soft and vulnerable. So that means that if you had blood rushing to your head, there's only one of two possibilities. Your head should actually expand because there's more volume of liquid in it, but it can't because there's a hard bone stopping it. Or you should be compressing that blood, into a denser form. But in fact, compressing blood, is incredibly hard to do, and it just doesn't happen, right? So this idea that there's more blood rushing to your head is also silly. So although it's a sort of a compelling story, and people believe that Mosso had actually done this, there's really no evidence to suggest that he could have possibly done such a thing or that it would give you anything meaningful. And that's the final thing. What would it mean? So let's just say those things were handled and Mosso had solved the issues that I've just addressed. What would it tell you? Well, it would tell you that when you think, your brain's involved, right? It doesn't tell you anything more than that. And of course, people in the 1890s already knew that. That wasn't something that was an open question. So the whole idea of this as the earliest form of neuroimaging is highly entertaining, and I think it's very engaging. And it's important to engage with it because you have to recognize why it's not correct, right? Why would this not make sense? What's fascinating is the exact same year, Roy and Sherrington, who were in Oxford at the time and were physiologists, were doing work with rodents, mice and rats. And what they found was that when you caused activity in a specific part of the brain, then there was an increase in local blood flow there. Now, mind you, there's a decrease in blood flow elsewhere to compensate so that there isn't a change in overall volume. So Roy and Sherrington said, these facts seem to us to indicate the existence of an autonomic mechanism which the blood supply in any part of the cerebral tissue is varied in accordance with the activity of the chemical changes which underlie the functional action of that part. It's a mouthful, but this particular observation from 1890 underlies all of the vascular functional neuroimaging techniques. So it's true for positron emission tomography, and it's just as true for functional magnetic resonance imaging. And I'm going to talk about that a little bit now. So I should just acknowledge from the beginning, I am not a physicist. That's not my background. I can give you an overview and an intuition for how the physics work, but if you're really keen on following this up, then what I would suggest is reading the relevant chapters in the Huettel Song and McCarthy book, because it goes into the physics much greater depth than I can do justice to in these lectures. But the important principle is that MRI relies on nuclear spin. So that is to say that fundamental pieces of matter, like atoms, or in this case, parts of atoms, so in this case, the hydrogen nucleus, which is just a proton, act like they spin. So the nuclear physicists actually do refer to this property as spin, and they assure me that it's not truly spinning, but nonetheless, that's a really good approximation. So that is to say that we have this little positive charged particle, a proton, which is, +1 positive charge, and it's acting like it's spinning. And the thing about something that's spinning, that's charged, is it's creating a magnetic field, right? So there's a current that's moving, and that causes a magnetic field based on Faraday's laws of electromagnetism. Because you're something like 60 or 70% of your body is made out of water, there's a ton of these free hydrogen nuclei running around your body. It's probably the most common single element in your body. And that's really useful because we can use the spin property in magnetic fields. Now, Under normal circumstances, you've got these, I'm going to say trillions, but that's way smaller than the actual number. You've got these enormous number of hydrogen nuclei that are spinning and acting like little bar magnets, but they're very randomly oriented. So that is to say, if one's going up, another's going down, it's going this way and that way, overall there's no net magnetic force in your body because they essentially cancel each other out because they're randomly oriented. However, if you put them in a very, very strong external magnetic field, like an MRI scanner, then what happens is on average they tend to line up with the field. So in this particular image, you can see that the magnetic field is going from floor to ceiling, and when you put the hydrogen nuclei within that field, on average they tend to line up that way. Now this is an oversimplification because you can see that all of them are lined up with the field in this image. That's not strictly true, but it acts that way. And at that point, once you're in the magnetic field, you do have a net magnetic property. Like you would be attracted to passing buses and things. Mind you, you're in a humongous magnet which would also be attracted to passing buses. So that's one of the reasons why the room is screened the way it is. And in fact, that's something we'll talk about in this week's lab about MRI safety. But at this point in time, you have a magnetic property. Your body has been magnetized. And what's happened is all of these molecules are lined up with the magnetic field, so they're in a very low energy state. They're very happy being lined up with the magnetic field. It is possible, however, to put energy into the system, assuming you do it at the correct frequency, to make those molecules jump from a low energy state, which is lined up with the field, to a high energy state, which is lined up against the field. And you can see that all the arrows have flipped directions in this case. So the field's still going up, but the individual atoms are facing down in terms of their spin. Now, this is intrinsically unstable. It doesn't want to stay in a high energy state. So what will happen is that they will give off radio frequency energy as they decay back to the low energy state. And that's what MRI is going to do. We're going to be able to input high energy radio frequency electromagnetism, right? That'll jump these hydrogen atoms from these low energy states to high energy states. And then they're going to decay back and give us some information about the nature of their decay by emitting radio frequency waves. So essentially we're going to have a radio receiver that allows us to record how that happens. If you were following along and thinking through what I've just said, then you've probably gotten the idea that, okay, so that's great, you can get a signal, but why would you get a different signal from different parts of the brain, right? All we've said so far is that you can input some energy, you can get some energy out, and of course it's coming from the head because that's the part in the scanner. But how is that different from what Angelo Mosso has said before in terms of it tilts the table up and down? That's which is exactly right, and is one of the very clever things about MRI, because the energy that you put in is proportional to the strength of the magnetic field. So the frequency that you put in is proportional to the strength of the magnetic field. So if you just have a single magnetic field, you put one piece of energy in, you get one piece of energy out. However, if you introduce gradients into that magnetic field, so that is you make it slightly weaker at one end and slightly stronger at another end, shown here, where it's sort of weaker at the bottom and stronger at the top, then what that says is that the frequencies that are coming out that are low frequency are going to be from this level, and mid-level is going to be at this point in space, and high frequency is going to be at this point in space. So in other words, you've encoded space in terms of the frequencies that are coming out of the scanner. And of course, if you can do it in one dimension, from, for instance, bottom to top, as shown here, you can do it in a second dimension, so front to back. And in fact, you can even do it in a third dimension, left to right, so that the frequencies that you're getting out of the scanner tell you where in space this signal comes from. And the signal is going to be dependent on the nature of the local environment. So water in fat is going to give you a different signal than water in like cerebral spinal fluid or water, blood, something like that, or water in bone, because there are different amounts of water in each place. They have slightly different chemical properties, and that means that as soon as you know where they are in space, you can then start to generate a 3D image of the actual underlying anatomy, and that's what I'm showing here. Now, what I've described up to this point is just magnetic resonance imaging, MRI. There's no functional part of this. What this does is it gives you a really nice picture of the anatomy, and it's relies on the fact that you can have very good spatial resolution. So a typical sort of research quality scan is about 1 by 1 by 1 millimeter, which is very good, because hospital scans are smaller or larger spaces than that. They'll be about 1 by 1 by 7 mil. But you can do better than that. You can get scans that are 800 microns by 800 microns, which is I'm showing in the top row here. So you can see, for instance, that in the top left, that's actually sort of a photograph of part of the thalamus, where you can see the lateral geniculate nuclei. Let me see if the cursor will show. And then the medial geniculate bundle. And this is an MRI scan of a person where hopefully you can see very clearly here, there's the lateral geniculate nuclei and that sort of paisley-shaped light area. And then just medial to that is the medial geniculate bundle. And you can do that because you can push the resolution to these very, very high levels. This is a really clear example from a study that a group in Oxford did, Holly Bridge. It's really cool. What she's looking at is the occipital pole here. So this is the calcarine sulcus, which is the site of primary visual cortex. But the thing about the calcarine sulcus is there's only part of the calcarine that's primary, and then it moves into secondary. And you can identify it based on, see that slight black stripe there? That's what's known as the band of Gennari, and it's a type of myelination that's occurring in V1, and only in V1. So at 300 microns by 300 microns, you can actually see that physical attribute of the cell layers, which is immensely impressive. Now, spatial resolution in structural imaging like this is essentially limited by how still a person can be. So you can imagine, like any kind of camera, if you're taking a picture of something, as long as it can stay still, you can get a nice clear picture. As soon as it starts bouncing around and moving, then you get blur to happen. Now, there's an intrinsic limit to how still a human being or any other living creature can be, because we have things like breathing and heart rate and all those kind of intrinsic processes that are going on that are causing our brains to move. Every time your heart contracts, it sends a high wave pressure through the carotid arteries into your cerebral arteries and causes your brain to move just a tiny little bit. So there is a slight limitation to how far we can push this, and 300 microns by 300 microns is a good example, about as good as we can get. It may be possible to do slightly better, but we run into physiological limits in terms of how still a human being can stay. If you're imaging postmortem tissue, obviously you can do much, much better, because of course there's nothing that causes it to move at all. Right, and here's just a sort of illustration in the scan that you can see the lateral geniculates in red and the medial geniculate in blue, just by pushing the resolution and the contrast in the image. So as I say, that's structural imaging, that's anatomical imaging, and it's no different in your brain than it is in your knee. If you blow out your ACL or something playing football, it's exactly the same type of MRI that's going to be used to get a nice picture of the soft tissues in your knee. But what we're interested in is functional magnetic resonance imaging, or fMRI, because we want to know not just what the tissue is, but how it's actually being used. And that depends on something called the blood oxygen level dependent signal, or the BOLD signal. And the clue here is in the name. What we're interested in is how blood oxygen changes the signal that we're actually measuring. But what that means then is, although what we're really interested in is neuronal activity, I mean, if we were to do this properly at some sense, we'd stick an electrode into the particular neuron of interest and we'd record its electrical activity, you know, at a millisecond by millisecond level. Not surprisingly, people tend to be a little bit touchy about sticking electrodes in through their skull and into their brain. So instead what we have is this kind of a non-invasive approach, where instead of us giving that kind of direct measure of neuronal activity, we're going to get an indirect index of neuronal activity that's based on blood oxygen levels and that insight that Sherrington and Roy had in 1890, which says that when a particular part of your brain is being used, then there's an increase in blood flow to that area. So there's more oxygen being brought to that area. And if we can detect changes in oxygenation non-invasively, then we can detect regional changes in activity of the brain, even if it's indirect. So how does this work? Well, it's predicated on the idea that oxygen is carried around your blood through hemoglobin molecules, and there's a sort of a 3D rendering of a molecule here. You can see that it has a set of subdomains that are in different colors. And what's important is that 4 of them have a single iron molecule at their heart. and that iron molecule combined with oxygen to carry 2 oxygen molecules around your blood. When it's bound, those oxygen molecules are essentially covering up that little iron molecule. Versus when it's not bound, you just have this sort of little free iron molecule in your hemoglobin. Think about what iron does in a magnetic field. So this is getting back to, when you were in high school or something and playing with magnetism for the first time. One of the things that they always show you is they give you this little bar magnet, they give you some paper clips, and they give you some iron filings. Now, if you just play with the paper clips on the iron filings, of course they're not magnetic, it doesn't do anything. But as soon as you touch that paper clip to the magnet, the paper clip itself becomes magnetic, right? And then that paper clip attracts the filings. This is exactly the same principle. When you put a human being, or an animal of any sort really, into an MRI scanner like this, the free is probably not the right term, the iron molecules that are not bound by oxygen in the hemoglobin act like little magnets, and they distort the magnetic field, exactly like the paper clip does when it's touching a bar magnet. When they're covered up by 2 oxygen molecules, they're essentially hidden, and therefore the iron doesn't affect the magnetic field. So what that means is that, I said earlier that the frequency gives you information about the space, right? So the frequency of the information is something that we can encode using external magnets, but as soon as you put something in the field that distorts the magnetic field, these free iron molecules within hemoglobin, then that changes the signal. It drops it because what it expects is distorted by the fact that there are these little iron molecules interfering with a magnetic field locally. In contrast, when they're covered with oxygen, it doesn't affect it. So in other words, what happens is that when there's oxygen that's being used from these hemoglobin molecules, that causes a little bit of distortion. There's a decrease in the signal that you see. So this is what we mean when we talk about blood oxygen level dependent. The level of oxygen in the blood at a particular point in space means that you have greater signal than if you have less oxygen in the blood at that space. Because if you have less oxygen, the lack of oxygen means the iron molecules in the hemoglobin are distorting the local field. Okay? This sensitivity to oxygen levels was first shown in vivo by a man named Keiji Agawa in 1990. And you can see, hopefully, that this is a rat brain. And what Keiji Agawa did was he had rats that were in 100% oxygen. So normally a room isn't 100%, it's like 20, 21%. So it was super oxygenating the blood of these rats so that anytime that their neurons were using energy, there was just a ton of oxygen there to replace it. And what he found was that if you then put the same rat in the same scanner and measured blood oxygen level signal, all of a sudden you can see the veins very clearly. So this is the bottom picture, the 21% or normal air. Because now, as oxygen is being used, it's not being replaced as quickly. So there's a loss of signal in the draining veins, right? So that is where there's blood that's already had its oxygen taken and is going back to the heart and the lungs to be reoxygenated. There's a drop in signal and you get these darker lines. And in fact, you can get a really nice picture of the venous-gram, the veins, in the rat in vivo using bolt signal. So to just sort of illustrate this in a little cartoon, imagine that you've got oxygenated blood, which is shown as these little red cells, coming in from the arteries into a capillary bed where there are neurons that are using some of the oxygen for firing. They need the energy, okay? And when it uses the oxygen, it then returns a blue or deoxygenated blood cell out of the capillary bed. So under normal circumstances, there's blood coming in, there's a sort of tonic level of neural activity that's using some of the oxygen and leaving some oxygenated and deoxygenated blood going out through the veins. However, if you then increase the local demand, so there was something happening there from before, but if you increase that, then it's going to draw more oxygen out of the blood, which means that there are fewer oxygenated blood cells and more deoxygenated blood cells going out through the veins back towards the heart, right? That only lasts for a very short period of time, though, because what Roy and Sherrington discovered was that your body responds by providing more blood. So it doesn't want to have a stroke, it doesn't want to collapse because there isn't enough energy. So what it does is it increases local blood flow, and in fact it gives you more blood flow than your local activity needs. So there's actually an increase in oxygenated blood very, very shortly after the increase in neuronal activity. And that means, by what we've just talked about, that there's an increase in bold signal as activity in the local area increases. And that change in the oxygen level of the blood indexes that increase in local neuronal activity. One of the consequences of this is that the signal that we're measuring, the bold signal, is slow because it depends on your blood. So despite the fact that your brain cells are reacting on a sort of a millisecond by millisecond level, or maybe it's tens of milliseconds if you think that that's a slightly more appropriate level, the blood flow doesn't respond that quickly. In fact, if you see a local increase in neuronal activity, it takes somewhere between 4 and 6 seconds for the blood flow to increase the amount of oxygen in those areas, just because blood is slower than neuronal activity. What's more than that is it takes up to about 21 seconds before the blood flow returns back to baseline levels. So if you just had something very focal happen in time that caused a spike in neuronal activity locally, you get this kind of characteristic hemodynamic response function that you can see on the plot, and it's slow. It's much slower than the neuronal activity that we're interested in. Nonetheless, that's what we've got, and that's what's important about the basics of the physiology of fMRI. Now, the very first human studies to demonstrate this were from Kwong and also Peter Bandettini. So I'm showing the Kwong study here on the left, and it's really hard to see this because this is the image that they actually reported in this paper back in 1992, when they didn't have any particularly good ways of visualizing these things. But these are what are called axial slices. They're slices in this plane, and hopefully what you can see is this bright area is visual cortex. So this is the back of the head and this is the front of the head. What was happening was Kwong was showing this flashing checkerboard. So there'd be 20 seconds of visual stimulation where a checkerboard would come on and off on the screen very rapidly. And then the screen would just go blank for another period of time. And then he would do another flash. And what you can see is that when he was flashing the checkerboard, there's this strong activity. There's more signal in occipital lobes and visual cortex. Whereas in contrast, when it was off, there's virtually nothing happened. And as soon as he turned it back on again, you get activity in visual cortex, and then it goes off and on, right? So it was a really clear demonstration that the brain was responding in a locally specific way to this change in visual stimulation in a way that was very plausible and made a lot of sense. And this was one of the very first demonstrations that fMRI was capable of measuring brain activity non-invasively in human beings. Pretty much at the same time, Peter Bandettini had a study where he did something similar, but instead of using the eyes and occipital cortex, he used the hand and he used motor cortex. So what Peter's group did was they had an experiment where people were lying in the scanner and they would get tapped on their leg, and as soon as they did, they had to sort of tap their fingers like this, right? It's not particularly complicated, but all of a sudden you're using motor cortex. And then they would tap them on the legs and they would stop. So what would happen was, if you look in motor cortex, so this area here in this image, you can see that when they're not tapping, activity is relatively low. And as soon as they start tapping, activity increases. But one of the things that you can see in the Bandettini study is this delay in time. The tapping started at this vertical line, but the actual increase happens about 5 or 6 seconds later. Similarly, the tapping stopped here, but it doesn't drop off for another 5 or 6 seconds. So this is one of those indications that started to get people aware of the fact that we were looking at these delays, and the delays were due to blood flow responses. So I've just covered a lot of material, but hopefully it's relatively clear and it gives you a little bit of a background for how we got to using fMRI, where it comes from, what it's actually doing. In the next lecture, what I'm going to do is talk about some of the more specific uses of fMRI as well as some of its limitations.